Hello again. In this lesson, we'll start to look at how transformations work with the equations for different functions and relations, specifically functions. When it comes to equations, what you're doing is you're comparing whatever equation you have to this general equation. Y is equal to a times f of k x minus c in a bracket plus d. The a, the k, the c, and the d are all different types of transformations. The a and the d will affect your y values in your table of values, and the k and the c will affect the x values in your table of values. And as long as you remember those things, along with the fact that the k and the c are always going to be opposite of what you expect, and we'll talk about that soon, you should be able to graph any transformation knowing what the parent function looks like. The first thing we should do is go over what all of those letters do. This is going to take a little bit of time, but it's probably a good thing to have at the beginning of whatever note you're looking at when you're talking about transformations. So let's talk about the a value first. I've written down here that if the absolute value of a is greater than 1, you have what is called a vertical stretch. So what does that mean? Well, the reason we're using the absolute value here is because a can do three things. It can stretch vertically, it can compress vertically, and it can also flip upside down. The flipping upside down can also be done with a stretch or a compression. So we have to take a look at a's value strictly as if it was a positive value first, and then talk about how the negative can also flip it upside down. So the absolute value here of a can mean greater than 1 would be a number like 2. 2 is greater than 1. But if you have negative 2 is under the effect of the negative sign as well as the 2. But all we're interested in here is what's the 2 going to do to the graph. And if you do the absolute value of negative 2, you also get a positive 2. That is also greater than 1. And any number whose absolute value is greater than 1 is going to be stretching the graph vertically. That's usually going to make your graph become taller and narrower. The other option, therefore, is what happens if a's positive value is not greater than 1, which would mean it's between 0 and 1. This would be a decimal value similar to 0.5 or 3/4. Again, just looking at the positive value of the a value, if you have this condition, you're going to have a vertical compression because all of your y values are going to be multiplied by a number that is a decimal between 0 and 1, which is scrunching them downwards, making them less tall and making your overall graph therefore wider. And the last case would be obviously what happens if a is smaller than 0. This would be a negative value for a, and I've already kind of mentioned it, that this is going to be what's called a vertical reflection. So your graph is going to be flipping upside down vertically. In certain textbooks, you might see a reflection in x or over x. The in x has always been a little bit confusing for me because on x, I've also seen in x, the way I'm thinking of it is you're looking in a mirror. So if the x-axis is your mirror, your whole graph is flipping upside down vertically. For the d value, and I'm starting with these two because they are the easiest ones, d is a vertical transformation again, and is specifically a vertical translation, which is a slide. So you're sliding the graph in an up or down direction depending on the sign of d. If d is greater than 0, meaning a positive value, you're going to be sliding your graph upwards. If d is a negative value or smaller than 0, you're going to be sliding your graph downwards. These are typically seen in grade 10, so this should be review of those concepts. Now the k value is different this year. It is brand new, but it is basically going to behave like the a value except for the x direction. So these are horizontal stretches and compressions. Now the problem is anything inside of the bracket with the x value is usually doing something that you're not expecting. It is behaving the opposite method that is being given to you. So you might see, for instance, the number 2 for your k value. The 2 would be multiplying inside of the bracket. So if I go back a screen here for a second, if you look at where the k value is right here, it is multiplying the x minus c. If k was equal to 2, your initial reaction would be to think that it's a stretch. But the problem is the k value affects the x values as a 1 over k relationship. So as an example, if k was equal to 3, you're actually going to do 1 over 3 times the x values, which is going to be squishing the x values towards the center or compressing your graph, making your graph, again, a little bit narrow. And we need to talk about the fact that sometimes a horizontal compression can actually look like a vertical stretch. And that'll come back a little bit more later. But for right now, you just need to know that if you have a k value that's greater than 1, again, it's the absolute value of k, because if it's negative, we'll talk about that in a second. But if you're looking at just the absolute value of k, if it is greater than 1, that is a horizontal compression. On the flip side of that, if k is between 0 and 1, it is a horizontal stretch. So it effectively behaves exactly the opposite of what the a value does, and it's doing it horizontally. But if you think of it as a 1 over k relationship, then a number like 1/4 for your k value, will be a 1 over 4 value, because you're putting a k value like 1 over 4. When you do 1 over k, you do 1 over 1/4, which is 1 divided by 1/4, which I've written this way, which is a little bit easier, I believe, to understand. When you have a division of a fraction, you flip and multiply, and therefore it would become 1 times 4 over 1, which becomes 4. So you're multiplying your x values by 4, which is stretching them. And the last thing that we need to talk about is when k is negative, that is a horizontal reflection. So now you're reflecting over the y-axis or in the y-axis horizontally, reflecting the graph. The last transformation we have to discuss is c. With c, because of where it is in the equation, again, it's going to be a little bit strange. When c is greater than 1, you're going to have a horizontal translation to the right. However, the sign in the bracket in a case like that will be negative. So if we go back to the general equation here, if c is positive, you'll be putting a number like positive 2 in there, but there's a negative sign in the bracket. So x minus 2 will make it seem like it's a negative 2. In other words, a negative in the bracket means you're actually moving to the right, because the c is actually positive. So again, it's the opposite of what you expect based on the equation's sign, but c would actually be positive, making it move to the right. And the opposite of that is if c is smaller than 1 or negative, if you put a negative inside that bracket, you'll have a negative negative, which will make it actually positive in the bracket. But because c is technically still negative, it is moving to the left. So anything that's an x transformation, you have to be very careful of because of that. So keep that in mind. If we now take a second to actually look at an example with an equation. So here's your first equation. You would have f of x is equal to 5 times the absolute value of 2x minus 4 plus 3. So I'm actually starting with an example that has all of the transformations in there so that we can discuss how they all behave. And the first thing you'd want to do is, looking at the parent function here of the absolute value, is use the table of values for that parent function. Now, what I like to do, you can do this in two different tables, but if you understand that there's going to be both x transformations and y transformations, you can leave some space here to do all of your calculations by giving yourself a little bit of room underneath the x part of the table, and same thing for the y part of the table. We are going to have to factor what's inside of this bracket. So I'm just going to give myself a little bit more room here. We have to factor out that 2 because it's not in the right format yet. So this is the correct format. And now we can see that the y transformations are the 5 and the 3. We could have seen that at the beginning as well, but the x transformations are the 2 here and the 2 here. So we need the table of values for our original absolute value graph. And if you go back to the previous notes for this section, the x values, we needed at least 1 negative, 0, and 1 positive, and the original y values are the exact same except without the negative signs. For the x values, because your k here is a 2, it's actually 1 over k that we're going to be multiplying by, or dividing by 2, if you will. So multiplying by 1/2 or dividing by 2 is the same thing. And we're also going to be adding 2 for the c value. And we're going to do that for all of them. Just to show you that multiplying by 1/2 and dividing by 2 are the same thing, I'm going to write the last one like that. So that those, you can write it in either way, whatever you prefer, but that's the way that that works. For the y values, we're going to be multiplying by 5 and adding 3 in that order. So for our new x values, we've got negative 1/2 plus 2. Well, that would be 1.5. And I'm just going to use the decimal value here because it's a little bit easier to manipulate, but you could definitely write it as a fraction if you want. 0 times 1/2 plus 2 is 2, and 1 divided by 2 plus 2 is 2.5. So that is moving to the right by 2, but then also having it compress, right? And then for our y values, we've got 1 times 5, which is 5. 5 plus 3 is 8. 0 times 5 is 0, plus 3 is 3. And 1 times 5 is 5, plus 3 is 8. And those would be the points that we would now plot to get our transformed graph. Now, I'm actually going to do this on Desmos because it's a little bit easier to demonstrate on Desmos and to actually see the comparison of the two. So let me switch over to Desmos at this point. So here in Desmos, I have written out the first table of values here in the first section of the Desmos graph. I've turned off all the other ones, and you can see the points for the absolute value on the graph itself, right, centered at 0, 0 here. Those are the parent values, and if I turn on the actual equation, you can see that the graph does pass through all of those points. If we look at the new points, here are where the new points would be. And if I turn on the equation for the actual graph that we were drawing, you'll see that the graph actually goes through those points. So stretched by a factor of 5 vertically, compressed horizontally by a factor of 2, which means multiplied all the x values by 1/2, moved to the right by 2, and up by 3. And this is the result of that. Moving on to the next slide, here is another way that function notation can sometimes be used. Sometimes it's used as a way to order the transformations that you want. Now, I put order in quotes here because I'm talking about like a restaurant order. So you're ordering a hamburger and fries or some sort of drink. Here, the transformation of the function is given as function notation. So you'll notice that the function itself is a square root function, but in the actual question where it says what transformations to use, they didn't write the square root in there, they just put the f function notation there assuming that you know that the function being used is the square root. And in that way, I could give like multiple different types of graphs that I'd want you to transform without having to write the square root each time. I could just put the f in that position. Or I could give you various functions, and you could just use the f to represent whatever those functions are. You can still see all of the different transformations in there. So you should be able to recognize that this -2 here is your a value, and that your x values are not quite written the correct way yet, that they need to be factored. And in this case, the only thing we could factor is a -1. So inside that bracket, we would have -1 times x minus 5. And at this point, you should be able to tell somebody what all the transformations are going to be. If you look at the a value, the negative means that it's a reflection in the x-axis, so a vertical reflection, and it's also being stretched by a factor of 2. For the x values, you have a k value of -1. The k value of -1 means it's going to be a reflection in the y-axis, so a horizontal reflection. K being 1, you're not going to be stretching or compressing horizontally. It's going to be the same general shape, but just reflected. And then you're also going to be moving to the right by 5. So again, you'd want to start with your table of values for a square root graph in this case. And because we have, again, both x and y transformations, we're going to leave a little bit of extra room for both of the columns. For the square root graph, 0, 1, 4, 9 are your starting x values. Square rooting those would give you 1, 2, and 3 for your y values, along with 0. And we're going to apply our x transformations. So it's a multiplication by -1 for k. That means we're going to multiply by 1 over k, or you can think of it as dividing by -1 for each one of these, which is going to be a reflection. And we're going to also add 5, which is going to be our horizontal translation. For our y values, we are simply going to multiply by -2, because that's the only y transformation there is. That is going to cause 2 different things to happen to the graph, though. It's going to flip upside down and be stretched by a factor of 2. So without even, well, I will be showing this on Desmos, but before we even get to Desmos, you should kind of have an idea as to what this graph is going to look like. If it's reflecting, so the regular square root graph looks like this. It's reflecting this way. It's moving to the right by 5, so it's going to end up being over here. And then it's also being stretched by a factor of 2, so it's going to get a little bit stretched like this, but then it's going to flip upside down vertically. So our final graph should look something like that. And again, we'll go to Desmos and see, but you should now be starting to be able to kind of predict what those changes are going to be. So going to Desmos with those tables of values, you'll see that I've got both the graph of root x and the table of values that gets generated from that equation showing here. I can turn off the equations just so you see the points. So that is your root graph. Now, when I do the table of values for the transformed graph, we get that for our points. And then if I turn on the graph for the transformed equation, you can see that that does go through those points. And I just want to point out that I'm not sure if I'm going to be able to do this with my pointer, but if you look at the original 0, 0 point, which is right here, it has moved over here, right, at 5, 0. If you look at this point here, which is a height of 1, 1, that point is here, and you can clearly see that it is twice as high underneath the x-axis, whereas the height here would only be a 1 for the first point. So it's definitely been stretched by a factor of 2, and it has flipped upside down. So my prediction of the graph being down below and being stretched out is correct. Obviously, I'm a little off scale, but it did give me a pretty good idea as to where the graph would be. Now, there are certain equations that we saw for our parent graphs that are a little bit different, and sometimes those equations can look strange when you have transformations involved. Looking at this equation here, f of x is equal to 3 over x plus 2 minus 1, can you tell what the parent function is? Can you tell which letter is 3, which letter is 2, and which letter is 1 in our or negative 1 in our transformations? So if you compare, and I'm going to write the actual transformed version of the equation below it here, sorry. So it looks like this. So which number represents the letter A in our transformations? Well, that would actually be the 3 here. Why? Well, because our parent function is the 1 over x graph. How did the 1 become a 3 in the new equation? Well, that is by multiplying the front of the equation by 3. But when you multiply a fraction by a number, you do top times top and bottom times bottom, so that 3 actually goes and joins the 1 at the top of the fraction, which might be a little bit hard to see from the original form of the equation here. The plus 2 should be pretty easy. It is next to the x, so this would represent our c, which would actually be negative 2 because you're putting it into an equation that has a negative in front of it already. And the minus 1 would be the d in that equation. So because this is the 1 over x graph, it does look a little bit strange in the equation, especially where the 3 is. The x being on the bottom of a fraction sometimes causes some issues as well, but as long as you just consider anything next to the x or involved with the x is going to be an x transformation, you should be okay. Using the table of values for that graph, we have both x and y transformations. So again, I'm going to leave myself some room on the x side, and there's always going to be room on the y side. The only points we had used were negative 1, 0, and 1, remembering that at 0 we have an undefined point. At negative 1 it is a negative 1, and at 1 it is a 1. So a quick reminder, this graph looks like this, and it does have horizontal and vertical asymptotes directly on the axes. So those horizontal and vertical asymptotes are going to shift with the vertical translations and the horizontal translations. So that's going to help us visualize where the graph is going to go. For our x transformation, the only x transformation is our c. So we're going to subtract 2, which is going to shift the graph to the left by 2. For our y transformations, we actually have both the a and the d, so we're going to multiply by 3, subtract by 1. Undefined is going to remain undefined. Multiply by 3, subtract by 1. And that'll give us our y values. So negative 3 minus 1 is negative 4, and 3 minus 1 is 2. So the graph is being shifted to the left by 2 and down by 1. And that's going to have the effect of changing the position of the asymptotes. So the vertical asymptote is going to be shifted left by 2. The horizontal asymptote is going to be shifted down by 1. And that kind of gives us an idea of where the graph is going to be, especially if we plot our points. Negative 3, negative 4 would be somewhere here, which kind of looks like the graph is going to end up being down there. And then negative 1 and 2, which would be somewhere here, kind of looks like the graph is going to be somewhere up here, and they're going to skim along the new asymptotes. So we'll use Desmos to show what that looks like. So here is the original table of values and the original equation both showing here. I can turn off the equation just to show you the original points. There are only 2 points, but we also know about the asymptotes, and those help us draw the rest of the graph. If I now show the new points where they are here. You can see that everything is shifted to the left and downwards a little bit. And if I turn on the actual equation of that transformed graph, you can see that it does go through those points. Let me turn off the other one. You can see that it does go through those points and that the asymptotes have been shifted. Now, it is kind of difficult to show every possible transformation scenario that you'll encounter. I've tried to show you a few of them with some of the weirder looking graphs as well as some of the regular looking graphs. The idea is if you can figure out the table of values or memorize the table of values of the functions that you're originally looking at, so the parent functions of the graphs, all you're doing is modifying the x values with any x transformations, modifying the y values with any y transformations, getting a few points that you can graph, and then drawing your curves through those points, taking into account any weird ones like these 1/x graphs. That's pretty much it. So try to remember that the x transformations are always kind of the opposite of what you expect. That's the hardest thing to remember, as well as memorizing your parent functions, and you should be good to go.